Robin shaving algorithm is designed especially for time-sharing systems. It is similar to first-come, first-served shaving, but preemption is added to enable the system to switch between processes. A small unit of time called a time quantum or time slice is defined. A time quantum is generally from 10 to 100 milliseconds in length. The reticule is treated as a circular queue. The CPU scheduler goes around the reticule, allocate CPU to each process for a time interval of up to one time quantum. To implement RR scheduling, we again treat the reticule as a FIFO queue of processes. New processes are added to the tail of the reticule. The CPU scheduler picks the first process from the reticule, sets a timer to interrupt after one time quantum, and dispatches the process. So let's look at this example. We suppose that all the processes arrive at time 0 in the order P1, P2, P3, P4. And here we give the CPU burst time for each process. And the time quantum equals to 20 milliseconds. Okay, so the Gantt chart is like this. First P1, because P1 arrived first, so first P1 get the CPU and execute for one time slice and be pre-inputted and put in at the end of reticule, and then P2. And we find that the P2 CPU burst is 17, smaller than the time quantum. So at time 37, the P2 terminates, then CPU scheduled P3 to execute. And after one time slice, at time 57, P3 is pre-inputted and put at the end of reticule. Then P4, after one time slice, then P4 is pre-inputted and put at the end of reticule. Then P1 again, and like this. At this time, we find that P4 only need 4 more milliseconds. So here, before the time slice, before the timer, that means the time slice arrives, the P4 finish its execution and terminates, and then the CPU is scheduled to P1 again. So from this Gantt chart, we can get the turnaround time for each process. You can see for P1 it is 134. For P2 it is 37. For P3 it is 154. Oh, sorry. For P3 it is 162. For P4 it is 121. We add these 4 turnaround time all together and divide by 4. We will get the average turnaround time. And the waiting time, average waiting time is we use the turnaround time minus the burst time. Then we get the waiting time for each process. Okay. So typically, higher average turnaround time than CPU, but better response time. The performance of RR algorithm depends heavily on the size of the time quantum. At one extreme, if the quantum is extremely large, the RR policy is the same as the first come, first served policy. In contrast, if the time quantum is extremely small, say 1 millisecond, the RR approach can result in a large number of context switches. Because you see in this Gantt chart, each vertical line represents a context switch. Because here, the CPU scheduler have to save all the status for P1 into its PCB and reload all the status for P2 from its PCB. So this is context switch. So each vertical line represents context switch. When we calculate the average around time, we omit the overhead for context switch. Okay, so if the time slice is extremely small, the round-robin approach can result in a large number of context switches. Assume, for example, that we have this picture. We only have only one precise of 10 time units. If the quantum is 12 time units, the process finishes in less than 1 time quantum with no overhead for context switch. If the quantum is 6 time units, however, the process requires 2 quanta, resulting in 1 context switch. If the time quantum is 1 time unit here, then 9 context switches will occur, slowing the execution of the process accordingly. Thus, we want the time quantum to be larger with respect to the context switch time. If the context switch time is approximately 10% of the time quantum, then about 10% of the CPU time will be spent in context switching. In practice, most of modern systems have time quantum ranging from 10 to 100 milliseconds. The time required for a context switch is typically less than 10 microseconds. Thus, the context switch time is a small fraction of the time quantum. A rule of thumb is that 10% of the CPU bursts should be shorter than the time quantum. Turnaround time also depends on the size of the time quantum, as we can see from this figure. The average turnaround time of a set of processes doesn't necessarily improve as the time quantum size increases. In general, the average turnaround time can be improved if most processes finish their next CPU burst in a single quantum time. For example, given 3 processes of 10 time units each and a quantum of 1 time unit, the average turnaround time is 29. If the time quantum is 10, however, the average turnaround time drops to 20. If context switch time is added in, the average turnaround time increases even more for a smaller time quantum, since more context switches are required.